Assalamualaikum and hello everyone. Today we are going to talk about the application of Newton's law. Generally, Newton's law of motion are the law that describe the relationship between the motion of an object and the forces acting on it. There are three laws, which are Newton's first law, Newton's second law, and Newton's third law. But today we are focusing on the Newton's second law. So, what is Newton's second law? When a force acts on a body, acceleration is produced. The greater the mass, the more force is required to accelerate the objects. Newton's second law said that the net force on a body is equals to the product of body mass and its acceleration. It expressed as the equation F equals to ma.
Hi, for this part we will discuss about our topic, which is Newton's second law. Before that, imagine that ball sitting on a table is a basketball or soccer ball. Pushing the ball to get it rolling should be easy, since it does not have a lot of mass. Now, imagine trying to push a bowling ball. You would need to use more force because the bowling ball has more mass. Newton's second law tells us something very important about the relationship between an object and its motion. A force exerted on an object causes it to accelerate, and the more mass an object has, the more force is necessary to slow the object down, speed it up, or make it turn. So now let's look at the question. A leaf of mass 600 kg is accelerating upwards carrying a man of mass 70 kg. If the tension in the leaf cables is 7,000 Newton, find the acceleration of the leaf and the force between the floor and the man's feet. When an elevator is moving upwards, it is moving against the force of gravity. Hence, a greater force is required to pull the elevator up. Let us derive the formula using the free body diagram above. The forces acting on the elevator are tension and weight of the elevator plus the weight of the person. The net force MA should be equal to the sum of forces acting on the elevator. So let's look at the calculation to find the acceleration and force between the floor and the man's feet in the next part.
Next, I will explain how we want to calculate for this question. From the question, we got the value of leaf mass equal to 600 kg, while the man's mass we got 70 kg, and the value of the tension also has given, which is equal to 7,000 Newton. The question also mentions that the directions of acceleration is moving upwards. So, the question asks us to find the acceleration of the leaf and the force between the floor and the man's feet. So, first step is we have to determine which formula is suitable for this question. How we want to determine it? We have to look at the acceleration's directions first, whether it's moving upwards or downwards. So for this question, the acceleration direction is moving upwards, which is the same direction with the tension. So I choose to choose this formula, which is T minus mg equal to ma. So we just have to substitute the value we got earlier from the question, which is tension equal to 700 Newton minus 670 and multiply with gravity. The value is 9.8 equal to 678, and we got the value of acceleration is 0.648 meter per second square. So, for the second question, it asks us to find the force between the floor and the man's feet. What we have to know first is there is a normal reaction force, which is denoted by R. So we have to use this formula, which is R minus mg equal to ma. We have to substitute the mass of a man, which is 70 kg, and multiply by 9.8, which is value of gravity, equal to 70, and substitute back the value of acceleration we got from the first question, which is 0.648 meter per second square. So we will get R equal to 731.36 Newton.
Based on the discussion, we can conclude that a man was pulled by the lift with the acceleration of 0.638 meter per second and the force of 731.36 Newton between the floor and the man's feet, and there is no doubt that everything happen in our daily life a little bit will involve in a mechanics or physics. By using a general formula, we can determine anything, even the weight of children holding a bottle and the force of a person pushing a door.